This is the introduction of our work, large-scale, low-cost 3D mapping AI technology through 2D LiDAR. Currently, 3D LiDAR sensors have been widely applied to capture 3D structures of the surrounding environment, especially for mapping services. However, the multi-beam 3D LiDARs are commonly expensive in price, large in size, and heavy in weight, which limit the LiDAR applications. Therefore, many organizations still hire surveyors to help them collect and measure graphics and position information by means of manual measurements. Finally, this data is used for map updates, land and property boundaries records, but this manual work is time-consuming and labor-intensive. It's very common to use satellites to build and update maps and measure distances, such as Google Maps. Although satellite mapping is more efficient than surveyors when the accuracy is less than a certain threshold, the commercial maps generated by satellites are unable to conduct highly precision-demanding tasks, such as autonomous driving. Driving mapping companies utilize expensive sensors to build and update maps. For example, Lyft uses 7 cameras and 3 high-beam LiDARs. For customized mapping services and frequent map updating operations, the existing solutions would be highly costly for wide applications. To overcome these limitations, we propose to combine images and low-cost 2D LiDARs to achieve highly accurate map building and sensor localization. Our solution, relying on the 2D LiDAR, is able to achieve highly precise and detailed 3D mapping and vehicle localization with a much lower cost. Waymo reports that LiDAR will play a key role to help self-driving vehicles to build and update maps in real time. Agricultural robots, especially UAV, will be critical to improve farming efficiency. The data collected by LiDAR can be used to estimate crop structures that can help farmers assess crop growth and predict yield. In environment monitoring, like climate change and water pollution, 3D maps from LiDAR can be used to estimate soil erosion and water storage. LiDAR 3D mapping can also be used on monitoring sea surface and structure underneath. The proposed 2D LiDAR-based technology estimates sensor motion and trajectory and builds the complete 3D map by applying sequential 2D LiDAR 3D mapping and sensor pose estimation as self-supervision. The geometric information of 2D LiDAR and the reconstructed scene is explored in this process. We first trained the deep learning simultaneous sensor motion estimation and 3D mapping network by sequential images to estimate an initial sensor motion and the local 3D maps. Then we apply the LiDAR to camera calibration metrics to online optimize the initial 3D maps. Finally, we explore the usage of a sequential 2D LiDAR sensing data as a cross-frame queue to update 3D maps of adjacent frames and generate the final optimized sensor motion trajectory and the complete 3D map. The 2D LiDAR and the camera are fixed on a platform, which are calibrated and connected to a computer in the vehicle. We show the sensor motion trajectory and the real-time 3D mapping on various scenes under the same sensor setting and methodology. A complete 3D map and the marked zoom-in regions are also demonstrated. Another city scenario is also tested. We drive on campus to build a campus map, including roads, buildings, and other surrounding scenes. We apply for patents based on the method to possibly commercialize our technology. Additionally, the team is collaborating with Ford Motor Company on a 3D sensing and reconstruction project by which we will explore its applications on autonomous driving, especially 3D scene reconstruction. The team has also received funding support from NSF to conduct research on 3D crop structure modeling and assessment based on 2D LiDAR. Outreach activities to farmers and agricultural researchers will be conducted to extend the applications of the proposed technology to agricultural domains. Thank you.